So let's review quickly enzyme kinetics so that we can better understand how inhibitors act. Generally, we study the activity of enzymes under Michaelis-Menten conditions. So this works very well when ES2P is the rate limiting step, and assumes that P concentration of P is almost zero, so that the reaction is essentially irreversible. The steady state approximation says that the rate of formation of ES is equal to the rate of consumption of ES. And so the concentration of ES, the enzyme substrate complex, is a constant. And so, in other words, that K1 is equal to the sum of K minus 1 plus K2. So the important parameters to remember here are Vmax, which is given by concentration of the enzyme total, multiplied by K2. And it's the rate that we have if all enzyme was bound to substrate, and generally this is a very, almost reached when basically the concentration of substrate is very large, and so everything gets converted to ES. The enzyme is saturated. Vmax and Km are obtained by plotting the initial velocities for a given, for a series of trials versus the concentration of a substrate, and that gives a parabolic curve. And so ideally we'll have several points here, initial velocities done at different concentrations of the substrate on the same enzyme, and this will define a curve, and then we can fit it to the Michaelis-Menten equations. Km relates to the affinity of an enzyme for a substrate, and so a small Km indicates a low degree of ES dissociation, so implies a high affinity between enzyme and substrate. And Km is basically the concentration of substrate corresponding to half of Vmax. This comes from the Michaelis-Menten equation that you probably have derived in biochemistry classes. The other important parameter is kcat, which basically is, most cases, is K2. This is often called the turnover frequencies, TOF, and it's the maximum number of substrate molecules that enzyme can convert to product per unit of time. It's derived from Vmax, because we know that the enzyme concentration. So Vmax is equal to K2 by concentration of the enzyme total. So not all the enzymes yield this kind of nice hyperbolic relationship, and so we have deviations from the Michaelis-Menten equation that in behavior that basically indicate either cooperativity in a multi-enzyme complex or the involvement of allostatic site on the enzyme. Also, many enzymes utilize complex pathways with more than one substrate bound. In other words, for example, they will need the presence of coenzyme and water. So this is it's important to remember that Michaelis-Menten is an approximation, and it's valid in specific conditions, in basically when ES is in steady state. If these conditions are met, then we can carry out the so-called Lineweaver-Burke realization to simplify obtaining Vmax and Km. And this was particularly useful before computers were available, when basically fitting numerically to the Michaelis-Menten equations was not possible. This is very useful though, and helps us visualizing and distinguishing the various steps of inhibitors. So if we plot 1 versus V, versus 1 over the concentration of substrate, we obtain this straight line where now the coefficient is Km over Vmax, and the intercept is 1 over Vmax. And so by doing that, is the intercept with the y-axis is 1 over Vmax, and the intercept with the x-axis is 1 over Km. The slope is the Km over Vmax. So with that, let's look a little bit more closely at reversible enzyme inhibitors. So the main differentiation here to make is between compounds that are reversible inhibitors and compounds that are non-reversible. For reversible inhibitors, in turn, we have two possible situations. We have binding at the active site, and so that will be a competitive inhibitor because competes with the substrate. Or we have inhibitors that act allosterically, so not at the active site, and this can be non-competitive or uncompetitive, depending on where they bind to the enzyme. In the most common situation in therapy, the competitive inhibitor binds reversible to the enzyme and results in effective lower affinity of the enzymes for the substrate. So, we have this situation for competitive inhibitors where the enzyme will normally bind the substrate, form the ES complex, which evolves to product. In the presence of a competitive inhibitor, we have an inactive enzyme. And so what happens is that the competitive inhibitor has no effect on Vmax because basically the enzyme ability to catalyze the reaction is unchanged, but has a large effect on Km because basically we will need a lot more substrate to form the same quantity of ES complex. And so the Lineweaver-Burke linearization that we just discussed allows us to visualize very easily and identify the type of inhibitor. In this case, remember, a competitive inhibitor undergoes no reaction. Ideally, good competitive inhibitors are designed to resemble the transition state. And that facilitates basically inhibition of the enzyme. We also have non-competitive inhibitors, which basically act at the allosteric regulation site. And so what happens here is that binding of the non-competitive inhibitor either prevents binding of the substrate to the enzyme or results in an inactive enzyme. So a pure non-competitive inhibitor will have no effect on substrate binding. But what will happen is that the enzyme substrate inhibitor complex cannot evolve to product. So Km will be unchanged, but we will have an effect on Vmax, and so the curve will change. The line actually will change in this way. We also have, more commonly in real life, a situation in which we have mixed non-competitive inhibitors, in which the inhibitor actually affects substrate binding as well, and so will have an effect both on Vmax and on Km. And that's the case for most allosteric inhibitors. Now, let's look at the so-called uncompetitive inhibitors. The effect of an uncompetitive inhibitor is on the Km of the substrate and on Vmax as well. So what happens here is that uncompetitive inhibitors bind the ES substrate and inactivate the enzyme. So they bind after the substrate is already bound. So this inhibitor-bound tertiary complex cannot form products, and so we have a decrease of both Vmax and Km by basically the same quantity. So the net effect of this uncompetitive inhibition is to decrease both the apparent Km and the Vmax of the enzyme.